Hello student, last class we have discussed what is Lorentz force and what the difference between electric force and magnetic force. Clear now? In this class we will go for motion of a charge particle in uniform magnetic field. Actually we have discussed two cases of charge particle, motion of charge particle inside magnetic field. So now again we discuss two cases. Case 1, suppose this is the direction of magnetic field B, and if there is a charge particle which is moving along the direction of magnetic field, so here theta equal to 0 degree. What is theta? This is case 1. What is the case 1? So our previous class we have discussed that is Fm equal to Q V cross B and its vector quantity. So its magnitude can be written QVB sin theta. What is theta? So here theta is angle between velocity of the charge particle and magnetic field. So here angle between velocity of the charge particle and magnetic field, because the charge particle is moving along the direction of magnetic field. So here magnetic force experienced by charge particle can be written, that is QVB sin 0 degree. And you know the value of sin 0 which is equal to 0. Now the force experienced by charge particle is 0. That means if it's the direction of charge particle which is a straight line, so the path here, the path of charge particle inside magnetic field, if charge particle moving with some velocity v along the direction of magnetic field, then part of this charge particle which is straight line, because it does not experience any force, it does not experience magnetic force, so its path is straight line. Clear? Second case, if this charge particle which is moving opposite to the direction of magnetic field, suppose this is the direction of magnetic field and this is the direction of charge particle which is moving with initial velocity v inside magnetic field, but here theta equal to 180 degree. That means the direction of flow of charge which is opposite to the direction of magnetic field, so here theta equal to 0 degree, sorry 180 degree. So according to magnetic force, that is Fm equal to QVB sin theta. So here theta equal to 180 degree, so you can write that is QVB sin 180 degree. And we know the value of sin 180 degree equal to 0. So magnetic force experienced by charge particle, the moving charge particle which is moving opposite to the direction of magnetic field, then the charge particle experience a magnetic force equal to 0. So in this case, the path of this moving charge particle which is anti-parallel or which is opposite to the direction of magnetic field, this path is also a straight line because it does not experience any force. So if charge particle moving along the direction of magnetic field or moving opposite to the direction of magnetic field, then the path of this charge particle, then the path of this moving charge particle which is a straight line. Clear? So now we will discuss here important case. If a charge particle which is moving perpendicular to the direction of magnetic field. So now we will discuss here. This is the direction of uniform magnetic field. In this direction of uniform magnetic field. Clear? Or we can take another one example. Suppose this cross indicate the direction of magnetic field which is inward direction and perpendicular to this field. Clear? This is the direction of uniform magnetic field which is inward direction. Clear? Now take one example. Suppose this is the direction, this is the initial velocity of a moving charge or positive charge q, and which moving with some velocity v, and this charge particle which is moving perpendicular direction, because this is one direction. Suppose if we take this is x axis, this is y axis, then this is z axis. Here the magnetic field which is in one direction and along z axis, but here the charge particle which moving with velocity v, and the direction of this charge particle which is along x axis. Clear? We know three axes, x axis, y axis and z axis are mutually perpendicular. So the angle between magnetic field which is in one direction and the velocity of the charge particle is angle 90 degree, because this is the direction of magnetic field and this is the direction of magnetic field in one direction, and this is the direction of charge particle v. So the angle between velocity of charge particle and magnetic field is 90 degree. So clear? So in this case we have to find, or we have to determine the path of this charge particle. Clear? Now to determine the direction or path of this charge particle, first we have to determine the direction of force, that means magnetic force. Clear? Now you can use left hand rule or you can use right hand palm rule. So what is right hand palm rule? Again you have to remember, this is the direction of magnetic field. The finger, the tip of the finger which indicate the direction of magnetic field, and the thumb indicate, or the thumb point the direction of electric charge, the motion of electric charge or the direction of current. Then the palm, this palm indicate the direction of magnetic force, this outward direction. Clear? So if we use this concept here, so this is the direction, look at the diagram, this is the direction of magnetic field which is along z axis, and this is the direction of velocity which is along x axis. Then according to right hand palm rule, this is direction of magnetic field and this is direction of velocity of the charge particle. Then the palm indicate the direction of magnetic force which is upward direction. Clear? So the intention of charge to move this direction due to magnetic force. What is the direction of magnetic force? So here the direction of magnetic force which is along y axis, because if you draw a clear diagram, this is x axis, this is y axis and this is z axis which is inward axis, this is z axis. Clear? And the x axis, along x axis the direction of velocity, and along y axis the direction of magnetic field. Clear? So the direction of magnetic force which always perpendicular to direction of velocity, the plane containing velocity vector and magnetic vector, that means the magnetic force which is along y axis. So here is the direction of magnetic field, is the direction of velocity of the charge particle, the thumb indicate, now the palm indicate the direction of magnetic force. That means the charge particle which experience a magnetic force in this direction, that means this is direction of F. Now the charge particle try to move this direction or intention to move this direction, due to this magnetic force which is upward direction, the charge particle which changes its direction, so in this direction. Now again if we choose this point, so at this point the direction, first we have to find direction of force. So here also magnetic field inward direction, the velocity which is this direction of charge particle moving in this direction, so force which is this direction. So this is the direction of magnetic force in this direction. Similarly, if charge particle then changes its direction, so here now force in this direction, so charge particle changes its velocity here, so force in this direction, so charge particle, and this is also coming from magnetic field, so then change its direction, so here this is also magnetic force, then here moving charge the velocity and magnetic force in this direction, so charge particle in this cross indicate magnetic field inward direction, so charge particle make a circular path, because the magnetic force which is inward direction and the magnetic force which is pointed towards the circle of the path. So if we make a clear diagram, this cross indicates the direction of uniform magnetic field. This is the direction of uniform magnetic field, and suppose this is the direction of a moving charge particle in this direction V, then it changes its direction, then the magnetic field, then the magnetic force uh, influence on the charged particle to move in a circular path. So, this is the direction of velocity at this point. This is also the direction of velocity of the charged particle, but in this point, this is the direction of magnetic force which is towards the center. And this is center point. This is cross indicate magnetic field. And if we choose this point, then this is the direction of magnetic field, and here this is the direction of magnetic force. Similarly, if you choose this point, this is the direction of velocity of the charged particle, and this is the direction of magnetic force. So these are the direction of magnetic force, and these are the direction of velocity. So in this case, here the magnetic field or the magnetic force only changes the direction of the charged particle, because this is initial direction of the charged particle. Now due to this magnetic force which is towards the center of the circle, now the charged particle changes its direction, but here magnitude remain constant. That means speed of the charged particle which is constant, but each and every point it changes its direction due to this force, due to this magnetic force, and the magnetic force which is inward direction and which is towards the center of the circular path. That means from this model we conclude that if a charged particle which is moving perpendicular to the direction of magnetic field, then the path of the charged particle is a circular. Then the trajectory of the charged particle is a circular. Clear? So here the magnetic force which influence on the charged particle to move in a circular path. That means here the magnetic force play important role to move the charged particle, to move the moving charged particle in circular path. So here magnetic force, that magnetic force here known as centripetal force. Centripetal force. So what is centripetal force? Centripetal force is the type of force which move a charged particle in a circular path, and its direction is always towards the center of the circle, and that force is known as centripetal force. We know the value of centripetal force, that is equal to mv square by r. Suppose this circular path, and if you take the radius of the circular path r, then mv square by r, which is equal to magnetic force. Clear? Second thing, this is the direction of charged particle. This is the direction of magnetic field B, and the magnetic field which was inward direction. This is the direction of magnetic field which is inward direction, and here this is the direction. This is the direction of charged particle. So, and the charged particle which is moving with velocity v. Clear? Here the velocity vector. This is velocity vector and magnetic field. This is the magnetic field and this is velocity vector. This is magnetic field and this is velocity vector. The angle between them is 90 degree. So we can write. We know the magnetic force Fn equal to QVB sin theta. What is theta? Theta is angle between magnetic field and velocity of the charged particle or velocity vector. But here the angle between velocity vector and magnetic field is 90 degree, because the magnetic field along the direction of this is x, y and z axis. The direction of velocity along x axis and the direction of magnetic field along z axis. So angle between x axis and z axis is 90 degree. So we can use here sin 90 and the value of sin 90 equal to 1. So Fm equal to QVB. Clear? So we can write here the formula, that is Fm equal to QVB equal to mv square by r, because this is the expression for centripetal force. So QVB, this is B only magnitude. 1 B here cancel. Clear? So you can write radius of this path can be write that is R equal to here MB, that is MB by QB, that is MB by QB. This is the expression of charge particle. If a charge particle which moving perpendicular to the direction of magnetic field with velocity v, and this velocity is perpendicular velocity. Clear? This velocity is here perpendicular velocity, that means this velocity is perpendicular to the direction of magnetic field. So radius of the circle can be represented R equal to M perpendicular component by QB. This is radius of the circle. Clear? Okay. So here the path of this charge particle is moving inside magnetic field and perpendicular to the direction of magnetic field with velocity v, and we can write the path of the charge particle here which is circular path, and its radius r equal to m perpendicular component of velocity divided by qb. You have to remember this relation, that is radius of the circular path, that is r equal to mv by qb. Clear? Now we will come what the time taken to complete one circle of the charge particle. If this cross the direction of magnetic field, uniform magnetic field B, and this is the direction of charge particle moving with velocity v plus charge particle, and this is the path of this circular path here, and this point center point, and this is radius r. This is the direction of magnetic force. Clear? Okay. Now we have to find time period of the charge particle. Time taken by the moving charge particle, time taken by the charge particle to complete one cycle. To complete one cycle, then we have to find total time taken by the charge particle. Clear? So what is time? We know velocity equal to distance by time. Now we have to find time. So time equal to distance by velocity. So time period we can write the time taken by charge particle to complete one cycle, which is equal to total distance traveled, the distance by distance upon velocity. Distance upon velocity of the charge particle, or distance upon the magnitude of this velocity. Clear? So total distance traveled by charge particle to complete one circle, which is equal to the circumference of the circle, and the circumference of the circle which is equal to 2 pi r divided by velocity, that is perpendicular velocity, that is v perpendicular. You can write, so that is equal to 2 pi into what is r? R equal to, we know, that is m v perpendicular by q into b divided by 2 pi r divided by v perpendicular. So here v perpendicular. Clear? So v perpendicular and v perpendicular cancel. Now the remaining part we can write 2 pi m, that is 2 pi m by qb. 2 pi m by qb. This is time taken to complete one cycle. Clear? Look at this relation. This relation which is independent of velocity of the charge particle, means the time taken by charge particle to complete one cycle which is independent of velocity. So this time equal to, it is 2 pi m by qb, that is independent of there is a small initial velocity is small, then the path will be small, then time, suppose this time taken to complete one cycle for small velocity, that is t1. Similarly, if I will take a large velocity, then it make a large circle, then time also t1. If velocity will increase, then it also increase its path, because radius r equal to mv by qb. If velocity increase, then radius of the circle increase. If we again increase the velocity, initial velocity, then the particle will make a large circular path, which make this time t1, this time t1, this time t1. Clear? So this time, which is independent of the velocity of the charged particle. Clear? Okay. Now, if you find frequency of the charged particle, what is frequency to complete one revolution per second? That is, frequency can be write. So frequency equal to 1 by time period, 1 by time period t. So we can write which is equal to 1 by this quantity, it is 2 by m by qb, and this can be write qb by 2 by m. This is the expression for frequency F equal to qb by 2 by m. So if a charged particle which moving perpendicular to the direction of magnetic field, then time period of the charged particle equal to 2 pi m by qb, and radius which made by the charged particle inside magnetic field, that is mv by qb, and frequency of the charged particle which is f equal to qb by 2 pi m. And here the time and frequency which is independent of the velocity of the charged particle. So far we have discussed, if a charged particle which moving parallel to the direction of magnetic field or anti-parallel to the direction of magnetic field, then the path of the charged particle is straight line. And if a charged particle which moving perpendicular to the direction of magnetic field, then the path of the charged particle is circular. Now we will go for, now we have to determine the path of the charged particle. If charged particle which moves any arbitrary angle with the direction of magnetic field, with the direction of uniform magnetic field. Suppose this is the direction of uniform magnetic field, and this is direction of uniform magnetic field B. And if we take Cartesian coordinate system, suppose this is x-axis and this is y-axis. Clear? And if we take suppose this is z-axis, x-axis, y-axis, and here this is z-axis, and here 0 0 0 origin, and this is the direction of magnetic field which is along the direction of x-axis. Clear? Okay. Now here there is a positive charged particle which moving inside uniform magnetic field with velocity v. This is uniform initial velocity of the charged particle. The charged particle is q, and which make an angle theta with magnetic field v. If we resolve its component along y-axis, if we resolve this velocity of this charged particle along x-axis and along y-axis, that is known as rectangular component. So here the rectangular component along x-axis can be write, that is v parallel component, and this component, because this angle theta, so its component along y-axis can be write v cos theta, because this component which is along or which is parallel to the direction of magnetic field, so can write v parallel component. Similarly, the perpendicular component which is along y-axis can be write v perpendicular, and this can be write the perpendicular component of v vector, that is v sin theta. So the velocity vector v, or the velocity of charged particle, it resolved into two rectangular component along x-axis and y-axis. and that component along x-axis which is parallel to the magnetic field, and that is V parallel equal to V cos theta. Similarly, its perpendicular component and its rectangular component along y-axis V perpendicular can be right, because this component which is perpendicular to the direction of magnetic field, so V perpendicular equal to V sin theta. Clear? There are two types of component. One component V cos theta along direction of magnetic field. Another one component V sin theta perpendicular to the direction of magnetic field. If we discuss about this component, first we discuss the component V cos theta, and this V cos theta which is parallel to the direction of magnetic field. If a charged particle, we know, if a charged particle is moving parallel to the direction of magnetic field, if this is charged particle Q and moving parallel to the direction of magnetic field theta equal to 0, then the magnetic force experienced by charged particle is 0. That means it does not experience any force if charged particle moving along the direction of magnetic field. Similarly, due to this component of velocity v, and this velocity does not change its direction along the direction of magnetic field, because along this direction the net force acting on this charged particle or net force acting on this component is 0. So it does not change its path, and the component V cos theta, this component does not affected by uniform magnetic field, and due to this component path is straight line. Due to this component, only horizontal component V cos theta, and due to this component the path of the charged particle is straight line. If we discuss about perpendicular component, that is V sin theta, then we will discuss about the component that is V sin theta. This is charged particle Q, positive charged particle, and here the component V perpendicular component, that is V sin theta. So if we discuss about perpendicular component V perpendicular, that is V sin theta, and here if there is a direction of magnetic field V in this direction, and this is the direction of the charged particle which is perpendicular to the direction of magnetic field, then the charged particle experience a force. Which direction? How can I know? By using right hand palm rule, this is the direction of magnetic field and this is the direction of velocity of the charged particle, then the direction of force which is in one direction. So here the direction of the charged particle, if this is z direction, the direction of the charged particle or the direction of magnetic force which is opposite to z axis, because three axes are perpendicular to each other, because this is the direction of magnetic field and this is the direction of the charged particle. Only if you choose perpendicular component, clear, this is the direction of magnetic field, so this is the direction of magnetic field along x axis, this is the direction of charged particle, motion of charged particle V perpendicular along y axis, but this is the direction of force, this is the direction, this is the z axis. So if we put right hand, this is the direction of magnetic field, this is the direction of charged particle, then the palm which indicate inward direction, and this is the direction of magnetic field, this is the direction of magnetic, this is the direction of magnetic force which is inward direction, and due to this component and due to this perpendicular component, the charged particle which make a circular path in this way. Only this component, only this perpendicular component, if this is the direction of magnetic field and this is perpendicular component, that is V perpendicular, due to this perpendicular component the charge particle make a circular path in this way. Clear? Because this is y axis and this is z, that means it is z dash axis, z dash. So the circle which is lies on the y and z dash axis, this is the circle. So this is the circle and this is the circular path of the charge particle and due to this perpendicular component here, and this is the radius of the charge particle. So you can write radius of the charge particle due to this perpendicular component can be write, we have that is m v perpendicular by q into b, we know, but here v perpendicular equal to v sin theta. So you can write here that is m v sin theta by qb. This is radius of the charge particle due to this perpendicular component, and due to this perpendicular component, the path of the charge particle which is a circular path. This is circular path. Clear? And this circle is two-dimensional figure, and this circle is lies on the plane. If this is z axis and this is inward as z dash axis, then the circle then it make a circle in this direction, and this circle which is x and z dash plane. Clear? So if a charge particle which move inside the uniform magnetic field at any arbitrary angle theta, due to its parallel component, the path of the charge particle which is straight line, that means this component, this is parallel component, and this parallel component does not affect by the magnetic force, and another one component which is perpendicular component v sin theta, and it experience a force, and this due to this magnetic force and the charge particle which make a circle, and due to this parallel component the particle which travel along straight line, and due to this component make a circular path. Clear? So this make a circular path. Due to this perpendicular component, charge particle make a circular path. Due to this parallel component, charge particle make a straight line path. If we combine to this path, then the resultant path of the charge particle can be drawn. Suppose we make another diagram, x axis, this is y axis, and this is about z axis, and this is the direction of magnetic field, uniform magnetic field B, and this is the direction of charge particle which making any arbitrary angle theta with the direction of magnetic field. This is the direction of magnetic field. Here, so there is two type of component. So first component here V parallel, that is V cos theta, and here perpendicular component, that is here perpendicular, this is parallel component, and here perpendicular component equal to V sin theta. And due to this parallel component, the path of the particle is straight line, and due to this perpendicular component, the path of this charge particle which is circular. That means look at me, click carefully. This is the direction of magnetic field. Due to this component, charge particle moving in this direction. Due to this perpendicular component, charge particle moving in this direction. Clear? So finally, if we combine to this path, then the final path of the charge particle will be like this. If there is no parallel component, then the path of the charge particle like this. Clear? That means this is initial point of the charge particle, and then also final point of the charge particle. Clear? But there is another type of motion of the charge particle which is along the direction of magnetic field. So due to this component, because it makes a straight line path, so due to this parallel component, the path of the charge particle will be like this. Clear? That means if there is no parallel component, then the path of the circle is like circular path. Circular path. If there is two type of paths, straight line path, this make a straight line, and this due to this component, that is circular. The combination of circular and straight line path, the total resultant path of this charge particle, this is in this way, and this path is known as helical path or path is known as helix. Clear? So what is helix? Helix is the component of straight line and circular. If there is only one component, that is parallel component, then path of charge particle is straight line. If there is only one component, that is perpendicular component, the path of charge particle is circular. If there is two type of vector, if there is two type of velocity, one parallel and one perpendicular, and due to this circling and due to this straight line, the combination of this path, the combination of this charge particle, the combination of this path will be helical, like this. And here moving x-axis, and here also making circular path. So this is helical path. This is the resultant path of the charge particle, and this charge particle is called the helical path. Clear? So if a charge particle which move at any arbitrary angle theta along the direction of magnetic field, then the path of this charge particle is a helix, and that path is known as helical path. Clear? And here the radius of this helical path, that is r equal to m v perpendicular divided by q into b. And if you use value, that is m v perpendicular to v sin theta, that is v sin theta divided by qb. So this is radius of the helical path. So radius of the charge particle in this case. If you find time period, what is time period? It is total distance. Total distance by velocity. So here also can write 2 pi r. This r here r equal to, we can be write here, that is m v sin theta divided by qb. But here velocity, that is perpendicular component, or we can write that is v perpendicular, and v perpendicular to v sin theta. So you can use here v sin theta. So here v sin theta cancel, only 2 pi m by qb. So T equal to 2 pi m by qb. Here also the time which is independent of velocity of the charge. Here, okay. Now if we find the value of frequency, then frequency will be like this. It is the frequency equal to 1 by time period. So you can find the value of frequency also here. Okay. Now next we will go pitch of the helix. Pitch of the helix or helical path. Now you have to understand what is the meaning of pitch. What is the meaning of pitch of the helix? That means what is pitch? So look at the diagram. We have to find pitch. Pitch of the helix. Look at the diagram. It is the linear distance or horizontal distance traveled by the charge particle in one revolution or in one time period. Clear? If the linear distance traveled or horizontal distance traveled by charged particle for one time period, if suppose there is only one component, perpendicular component, if there is no parallel component, then path will be a circular. Then what is time period here? Time period means if this is the starting point here and this is the final point here, this is called one time period. Clear? But there is two type of paths, circular path. One is straight line path, and here in this case, due to this perpendicular component, the path of the charged particle is circular, but due to this parallel component, the path of the charged particle is straight line. So if you combine to this path, then the path of the charged particle helix. So due to helical path, this is initial point, clear, and it completes a circle. This is helix, and it completes a circular path here. Clear? This is one cycle. So for one cycle, and this distance is known as pitch. That means if charged particle starting here, this point, then this is the point in this way. In this way. So this distance, imagine this is the initial point and charged particle make a circular path, and due to straight line path we make a helical structure like this. Clear? So the helical structure like this. So the pitch, what is pitch? It is the linear distance and horizontal distance traveled by charged particle in one time period. So if it's starting this point, then this is the helical distance. Clear? To complete one revolution, and that is called pitch of the helical path. So pitch can be right, and that is what is pitch? That means velocity equal to distance by time, and this is the distance pitch. Pitch means linear distance traveled by particle to for one revolution, for one time period. So distance equal to velocity into time, but here velocity equal to parallel velocity. So here that is v parallel into time, total time t, can write t. Clear? Now if you use the value, that is v parallel equal to, here v parallel equal to v cos theta. So here v cos theta into total time period t, and here total time period equal to 2 pi m by qb. So you can use here, that is equal to v cos theta. So v cos theta into 2 pi m by qb. Clear? So this is pitch. Clear? So total pitch, that is pitch equal to parallel component in total time period, and that is equal to v cos theta equal to 2 pi m by qb. Or we can write here pitch equal to, I can write pitch p equal to v cos theta, that is 2 pi m v cos theta divided by qb. This is called pitch. So what is pitch? It is the linear distance traveled by the charged particle for one revolution. Or it is the linear distance traveled by charged particle to complete one revolution. Suppose this is the circular path. This is circular path and time taken t. But here there is two type of path, circular path and straight line path. So this path can write, the particle try to complete this path. But due to this linear motion, the particle changes. The particle will be like this. Clear? If we take the time t, then if we take the time t to complete this circle, total time t, if along with this line, you can write this total time to complete this line in C, then this can be written as pitch. That means for one time period, the linear distance traveled by the charged particle is known as pitch. So pitch equal to 2 pi m v cos theta by QB. Clear? So this is all about if a charged particle moving parallel or anti-parallel to the direction of magnetic field, then path of the charged particle is straight line. If a charged particle which is moving perpendicular to the direction of magnetic field, then path of the charged particle is circular. And if the charged particle move any arbitrary angle along the direction of uniform magnetic field, then path of the charged particle is helix. Clear?